just about a week ago, and Steve and Sungjun had about 4 days to set up our software, basically from the device driver level on the OP. So what we wanted to do was kind of just briefly relate how we approach putting software onto the OP platform, and just some of our experience in terms of, and to show you some example code in terms of how we see it as kind of both a research and educational platform in terms of the software perspective. So what I wanted to just do is, we have a lot of kind of robotics projects at the University of Pennsylvania, various types of robots. We have robots that work outdoors, that work using cameras and autonomous navigation in outdoor environments here. So this is a robot that just shows kind of how it can kind of, using stereo cameras, be able to plan and navigate through this kind of very rough and outdoor terrain. We have, we were also involved with a robot called Little Dog, which is built by Boston Dynamics, which is modeled after Big Dog. Here again, you had to develop software to enable four-legged locomotion across this kind of very rough terrain using planning and perception navigation to basically choose your footsteps and be able to then plan your way across such a kind of a terrain board such as this. And so here you see kind of how the software is kind of viewing this and being able to place its feet in the right place. We also had projects involving teams of robots. This is a heterogeneous team of robots that we took to Australia that have to search and to use LiDAR scanners as well as cameras to find and see obstacles in the environment, in a very kind of dynamic urban environment. We also had these autonomous cars. So we had a little Toyota Prius that was instrumented to basically be able to use LiDARs and cameras as well as the navigation units to be able to kind of maneuver through these kinds of dynamic environments. So this is just a sequence here from our Urban Challenge vehicle. Here the computers are controlling it. It's behind this, one of the human drivers in the Urban Challenge that we did with Dennis. Here you come up to a four-way stop sign intersection. So here you stop at this intersection. In this case, there's another car waiting at this intersection. So the software here is kind of knows that there's another car at that location. It's a four-way stop, so we're waiting for that robot to move. Unfortunately, that other robot is kind of, I think, disabled, so it's not able to go through the intersection. So our software immediately says, okay, you're allowed to wait 45 seconds, I think, before you can go out of turn in this four-way intersection. So then the software takes over control of the car here, makes a right-hand turn. Unfortunately, when we make this right-hand turn, there was another robot that tried to pass this robot, and so it's stuck in the wrong lane. So as you see the software, you see now that there's another robot in our lane. We turn. You see all the human drivers. One of these human drivers backs up. That gives enough room for the software to say, okay, now it's time to pass this car. So now it goes into a pass mode, goes around this stuck robot, and then continues along the rest of the mission. Right? So this is the type of autonomous behavior that you want to be able to have the students be able to build into these types of intelligent robotic systems. Okay? So in our experience with these types of systems, what we're seeing is that in order to kind of get a good working software, you really want to think about a kind of a nice hierarchical decomposition of all your algorithms and modules. And so the way we structure the common themes with all these types of systems is that you want some sort of a very efficient low-level C++ interfaces to all your devices, right, to your sensors and your actuators. So we write that in C++, but immediately then we try to go to a higher level type of programming language. So in our case, for all these robot systems, we've used a combination of MATLAB, which is which I think a lot of engineering students have good experience with in the classroom. So we use MATLAB, or a completely open source solution, which is another scripting language called Lua, which is a very compact, very fast scripting language. And so what we're doing is that we have kind of this separation between low-level types of interfaces using C++ and high-level things in these scripting languages. If you want to go fast and efficient, we make these dynamical loadable libraries that the scripting languages can call so that they can do basic computations at a very fast speed, such as if you need to speed up your vision processing or you need to speed up some sort of kinematic computations, we make those dynamic loadable libraries that can be called by MATLAB or Lua. And then what this results in is that the students can interact with the software without having to do this kind of, as you saw, the recompilation, the retest, the reboot. Sometimes you have to reboot the robots. You can just kind of restart your script, and you can now easily kind of try to change things on the fly. And so this allows us, and if you have the right tools in terms of being able to visualize your variables and your interfaces, if you can do this very efficiently, then you can very quickly develop software without having to kind of do this very slow debug cycle. So what we've shown here is that we've taken this approach and we've actually implemented it now in terms of the University of Pennsylvania on a variety of platforms, including the NOW, the MiniHubo, the Darwin LC, as well as the DARwIN-HP from Dennis's lab, from the Roma lab. So what we wanted to show was kind of the two approaches, and just to introduce that. So one way that we do is we just basically take the processor here, this Atom processor, we just download, we put MATLAB on it, and we can actually run full-blown MATLAB. Then all our accesses to the Dynamixel to move a motor is just a MATLAB function, like move motor to a certain position in MATLAB. Or if you want to grab the camera image, we just call a single MATLAB function, which gives us an RGB image in MATLAB that you can then plot on your screen through your VNC, and you can now actually do image processing just directly on the robot by doing kind of MATLAB functions. Right? So this is one way that we developed the robot. What Steve and Sungjun will show you is because MATLAB is, you actually have to buy MATLAB, you have to have your own license for it to work. We have now a different scripting language called Lua, which is a very small, compact language. And this allows us, in this case, we have a Lua interface which is that goes into our simulation environment. This is a Weebot simulation of the NOW robot. And so what we have done is basically made our Lua interface exactly the same for the robots as well as these simulators. And so what we can just do is write all your code in the simulation or in the robot. You put that on the robot, and then you can boot them up in the robot, and then you can kind of debug and to graphically see what's going on. So just to show you how it looks on the simulator before I turn it over, what I can do here is if I run in the simulator, this is kind of what the environment looks like. You run, in this case, the Weebot simulator. Right, so what the Weebot, the simulator gives you is a model of the robot with the open, dynamics engine, open dynamics engine that does the physics simulation, the graphics, and then we just have a Lua terminal here, and then we can just run our little Lua script that basically calls high-level player behavior here, which basically takes in the camera images here, and now is actuating going through the inverse kinematics, doing the inverse kinematics, doing the walk, and then basically you have now kind of an interface into seeing how well these scripting, how well your behaviors, your low-level algorithms, your vision algorithms, you can easily debug them in this kind of environment. Okay. So what we have now then is, what I wanted to do is actually, because of the full power of the OP processor, you have the graphical environment, which a lot of robots don't give you. You just get some sort of text environment. You have the graphical environment. You can run full-blown Linux programs or Windows programs. If you install Windows on this, you have now basically a full power of doing all this right on your OP platform. And so let me turn it over now to Steve and Sungjun, and they'll lead you through kind of how we structured our software. We'll also make this completely open source. So if people want to start with this framework, instead of the kind of the complete C++ framework that Robotis has, they're also welcome to do whatever they want with our code and to be able to start very quickly. So, Steve.
Thank you very much. But before that, I think it's important for us to take a quick break.
Yeah.
Right? A 3-minute break?
Great.